Hi. The final step in putting together the OPO, OPA system is to mount the crystals on the different motors in the system and orient them, and then do the calibration for both the OPO and the OPA stage. Now, for mounting the crystals, each one of them is on a mounting block that has a set screw for the motor post. You'll need to be putting these on at a fairly large angle so that you can access the set screw. Once all the crystals are on, you can use the program to go in and rotate each of the individual motors until the crystals appear to be at normal incidence. For finer tuning of the system, you want to use a beam for reference and look for the back reflections off the surfaces to determine exactly what normal incidence is. For the OPA stage, I prefer to use an external Heaney laser that I bring in through the two alignment apertures that are centered on the beam axis in the system, and place a vertically lined card with a hole in it in the beam so that the Heaney is just passing through the hole. What you'll see is 4 reflections here that are from the face of each one of the crystals in the system. You'll notice that the reflections are both above and below the main incoming Heaney beam, and that's because the crystal pairs are each oriented such that the first crystal is tipped backwards, the second crystal is tipped forwards. This is to avoid back reflections of the 1 micron to the pump laser, and hence you see 2 spots above and 2 spots below. When these spots are in vertical alignment, the motors are at normal incidence, and you should go into the setup window for each of these motors and set their position reading to be 0. Okay, for the OPO stage, I like to use the green light that is already been aligned to the axis of the OPO, OPA stages. What I like to do is I like to do this at low energy with the input aperture closed down to make a nice small green beam to see. On the first pass through the system, the beam will impact HR3, and a small portion of that green will leak through to the back wall, which I'll see on a card here. The beam then double passes through the crystal, is returned back to the entrance aperture, but a small portion will leak through HR3 and reflect off the grating to the rear mirror in the system. To do the orientation for the crystals, I'll take this rear mirror out by loosening the post holder set screw and setting the mirror off to the side, so I can use another lined card to look for the main leakage through from the returning green, and then the reflections from both the front and the back crystal faces. And I'll show you what that looks like here. So I've got the mount off to the side. Right here we can see the main beam is the brightest spot, and then there's 2 spots above and 2 spots below. Each crystal has 2 spots, one is above and one is below, and these rotate in opposite directions as you tune the crystals. When these spots are all in vertical alignment, the crystals are at normal incidence, and you'd want to go in and set the positions to 0. Okay, now for putting the rear mirror back in again, you want to put it in place so that it is reflecting the green light back off the grating again. That will all be reflected by HR3, and you'll see a second spot on the rear wall. There is another configuration for the rear mirror if it's a little more clockwise rotated, you can miss the grating and also see another spot. So just make sure that the spot you're seeing is the one that's reflecting off the grating. What you'll see on the rear wall is two spots, one from the first pass of the green through the system, and the one that's being returned by the rear mirror. And you'll also see the extra spots from the crystal reflections as well. So you'll want to adjust the rear mirror to get the two spots to coalesce on top of each other. If you have your injection seeder on, you can open that up and then turn that on and then open the aperture of the system, and you'll be able to see interference fringes when the alignment is very close. The fine tweaking of the rear mirror is just to adjust it so that those fringes separate out until you're at the center of the interference pattern. The only reason to set the crystals to read 0 at normal incidence is to give you a reference point for the system. If you ever put crystals in or take them out, you can always find the normal incidence position. The program for the narrowband systems like this does not use the actual physical reading for the motor position. It's only mainly for your reference in the system. At normal incidence, the oscillator stage is running at around 803.5 nanometers, and the amplifier stage is set at 745 nanometers. I'm going to first calibrate the OPO stage, and so I'm going to deactivate the OPA motors, leaving them parked at 745 nanometers, so I can come back to that wavelength later and pick them up. You can do that just by going into the settings menu here and changing the number of motors in the system to 3. Okay. My calibration is not done simply from scratch, orienting the crystals in the tuning mirror and such to get maximum energy and then measuring the wavelength. I do have other systems that I've built identical to this, and so I'll start by using an older set of coefficients for all of the motors in the system. I'll enter that into the program, and that will be my beginning point for doing the calibration in the system here. The tuning behavior of the OPO stage is each of the motors in the system have nearly a linear relationship with position versus wavelength in the system. And I can show you from the coefficients that I'm using. This is what motor 1 looks like. Position is a function of near-infrared wavelength. Motor 2 and motor 3, which is turning the opposite direction, of course. Those are very nearly linear lines. But if you subtract off the linear component of that, you'll see that there is actually a little bit of deviation from linearity for these motors. The reference point here again was for motor number 2, position of 0 was corresponding to around 803.5 nanometers. So with both of the crystals at normal incidence in the oscillator, they're very close to their operational position. All I need to do is rotate one of them, and my choice is always motor number 3, the second crystal in the system, to find the maximum of energy in the broadband mode. A more difficult positioning to find is that for the tuning mirror, which is determining the wavelength in narrowband mode. But what I do is as a reference point is to cut out an angle on a card that is at the correct angle between the tuning mirror and the grating, and then use that for to initially orient motor number 1, the tuning mirror position. So the grazing angle is 5.4 degrees on the grating, and the angle that I calculate for 803.5 nanometers for the between the tuning mirror and the grating is 26.79 degrees. So I can just hold this in place and visually orient the motor number 1 until the tuning mirror is nearly at the correct angle. Then I can spend less time searching around to find the optimum position. When optimizing the system, I found that you get a much better calibration if you place your power meter not right after the OPO or at the output port, but about 50 centimeters from the output port, centered behind an aperture, about 7 or 8 millimeter aperture that's centered on the green leakage from the OPO. That is the best position to actually do the calibration for these systems. So I'll start this up in just a second, but the procedure that you go through is to start with a broadband mode by covering up the grating, and so that you're just getting broadband oscillation between the two, the rear mirror and the output coupler. I then rotate motor number 3, the second crystal, to find the optimum energy of the output. I'll then block the rear mirror, uncover the grating, and find the maximum in position for motor number 1, and then record those positions. The program makes it very easy for you to record the values. If you go into calibration, you can see there's this record positions. The equivalent would be to press the F4 key, and a window will pop up and it will ask you what the measured wavelength is. It comes pre-populated with the actual wavelength that's displayed. So if you're using a wave meter to determine the wavelength of the output from the oscillator, you can enter that value in. What I do is slightly different. These crystals are all very reproducible, except for a slight offset in the crystal angle, depending upon how the grower has done the final cut. And so I use calibration coefficients that I've derived from using wave meters in other people's labs, and invert that so that I can use the position of the first crystal in order to determine what the operating wavelength is. Any way that you do it, you need to be able to somehow determine the wavelength of operation of the system. You can trust the tuning mirror value, which is the value that's actually displayed on the for wavelength in the system, or you can do like I do and use some other reference point. When you press save, the program will write those positions out to a file called moparam.dat, and this is what it looks like. If there's already data, if the file already exists and there's data in it, the program will just append the wavelength and then the positions of each of the motors in the systems to that file. If you're going to be starting a brand new calibration, it's best to clear all that data out or just delete that particular file, and a new one will be created when you press the F4 and save key to record the motor positions. So, before beginning the calibration, you should let the oscillator warm up for about 5 minutes while pumping with full energy. This is because, small amount of the green is absorbed by these crystals, and they need time to get to thermal equilibrium. The temperature of the crystals does slightly affect the tuning behavior, and so you'd like them to be at the operating temperature. Now, I'll take that time. I've got the beam to the power meter block, and so I can set the 0, go into the power meter function here, and you can see I've got the correct unit scale here, and we're very nearly 0, so I'm not going to adjust that. I can start recording at any time. It's collecting data, but nothing is happening because the near-infrared wavelength's not changing. Go to motor number 3. Unblock the beam, and I want to start with the tuning mirror blocked and the rear mirror unblocked in broadband mode to optimize the second crystal in the system. So little blip from my electronics. Now you'll notice that the forward and backwards curves are offset slightly from each other. This is predominantly due to the fact that I'm using a thermal power meter, and there is a lag time in its response. So the best spot for positioning the crystals is always going to be right centered between the two descending lines on for each of the curves. So right about there. Okay. Now I can move on and do the tuning mirror. Just go into motor number 1. That's annoying. I hope your power meter doesn't do that. And I would choose that as the, maybe a little bit more over, that as the center point. Okay, so now I've got the oscillator up and running at 803.5 nanometers. The next step for calibrating the oscillator, I like to go down to the beginning of the tuning range at 710, and then take data points every 5 to 7 nanometers all the way out to the end tuning, which is at around 880 nanometers. This gives me a great collection of data, but first I'll need to scan down to 710 to begin the calibration. So the nicest way to do this is to bring the power meter back up, go into start recording, and go into the spectrum mode here. And so you can see the energy is a function of wavelength. And then begin scanning the oscillator down to, I'll go to 709.8. and you can keep track of the energy then as the system is tuning down. For the most part, the calibrations, the earlier calibration that I'm using for the system should be very close, and so I shouldn't see a significant fall off in power. But if I do, what I would do is stop the scan, re-optimize motor number 3 in broadband mode, and then re-optimize motor number 1 in narrowband mode, and then continue on down to 710 so I can begin the calibration run. Okay. Once I've stepped through the full calibration range and collected the data using the F4 key to record the wavelength and the motor positions for motors 1, 2, and 3, I can go through and calibrate the data. So this is actually the file that I used for calibrating this oscillator. Let me go into calibration, generate fits, and select that file. Copy.dat. And you'll be given the option for each one of the motors as to what polynomial order you'd like to use for the data. So if I can go to linear subtracted here, I can see the curvature. The red line is a spline fit to the data, and the green line is a polynomial fit. And so I can change the polynomial fit and observe what that does to the actual curve that is going to be followed by the motors, and what the statistics say about that. Usually a ninth order polynomial is best fit. The spline fit is actually quite nice because it can follow the actual behavior of the motor positions that you measured. And so any slight deviations that aren't taken care of by a ninth order polynomial can be fit by the cubic spline function. Now you can choose which curve you're going to be using in the setup window for each one of the motors. The really nice feature for using the spline fit is that the motor stops tuning if you go outside of the wavelength range. If you're using a polynomial curve and you go outside of the tuning range, the polynomial can just blow up and the motor will start spinning out of control. But if you've only got data over a limited range, like say for the silver gallium selenide crystal, which is only usable from like 724 to 762 nanometers, you would be better off using the spline fit so that the motor doesn't accidentally spin out of control if you leave it open while you're tuning. The spline fit will just stop the motor from moving once it's outside of its range. Okay, so I can step through, look at each one of the motors. Motor 2, that looks really nice because of the way that I entered in the data for it. Entered in the wavelength data. And motor number 3, linear subtracted, you can see a little bit more noise in there. And that's done. It's going to ask me for a name for the files, and so I can do this as just like poly.fit. Okay, and now that's those files have been written out to the LaserVision directory, cubic.fit, poly.fit. To enter in the coefficients, I'm going to want to close out the program first, then open up, say for the polynomial coefficients, the calibration file writes it out exactly as the mid-ir.dat file, which has the motor coefficients into it. So all I need to do is copy and paste. I'm not going to do it, but copy and paste those new values into midir.dat. The same is for the cubic fit file, which is in the same form as the data file for the cubic fit data. So you can just select and copy the data points and enter them in. When you restart the program, the new constants will automatically be loaded. At this point, I want to go and pick up the OPA crystals. So I've scanned down to 745 nanometers so that I can begin calibration of the OPA stage too. So very first thing, I've been blocking the 1 micron pump for the OPA while I did the measurements for the OPO. But I can unblock this now. And of course we're off scale here. Okay. For calibration of the OPA stage, using the same configuration, same aperture, set it on the green leakage from the OPO with your power meter placed behind it at a distance of about 50 centimeters from the output port is the best for the system. Now you want to make sure that the wave plate is set at 45 degrees, which is going to be optimal. If it's turned down to 0 degrees, you won't find much conversion at all. Okay. So let me step through each. These OPA crystals do not need to be warmed up because there isn't any absorption at 1 micron for them. So let me first activate the OPA crystals. Okay, and go into the power meter. I'm using 1 watt full scale now. Let me 0 that. Okay, close enough. Now I can begin by optimizing each of the crystals. So power meter, let's start recording motor 7. I like to start with the last motor and move in towards the first crystal. You notice you will see some oscillation after the main peak. It's mainly pronounced for motors 5 and 6. Okay, that would be what I would call the best position. Go into motor number 6. Motor number 5. And I'm going to go a little bit farther from motor number 5 so you can see what happens outside of the range. That you'll just continue to see oscillations as it comes in and out of phase. You don't want to get confused that by trying to optimize on one of these peaks, because it's not the primary peak. It should be coming up right here. I'm going to base my choice by straddling the position of these two curves here on the inside. Okay, so that was just the first pass through the OPA crystals, and you can see how much I needed to adjust each one of the crystals. Minus 38 counts for motor number 4, minus 22 for motor number 5, plus 55 for 7, and plus 17 for 6. This is a reasonable range for the crystals to be off in. So I don't think I can improve on this, but there are some aspects you want to check about the output of the beam. For one, you want to have both the signal and the idle are collinear on the output. But by repositioning these crystals, I can force a non-collinear behavior. And so let me just stop and set this up, and I'll show you what that looks like. Okay, I've removed the power meter and placed a silver mirror to reflect the beam back over a distance to this white card that I've got on the other laser table over here. You can't see it, I don't think, but there's a green spot there. This is green that's caused by the 1 micron in the OPA crystals. The weak green is just non-phase matched harmonic generation in these crystals. I've also turned down the green from the OPO so that it's about the same intensity. And so if you could see it, I can block and unblock the oscillator, and those two spots should be overlapped. If they're not overlapped, you need to adjust the last mirror, 1 micron mirror before the OPA stage to get the two spots overlapped. This will give you a collinear phase matching, hopefully. Now, when I turn the oscillator back up again, I'm going to be getting the full output over at the white card. So let me just so it actually looks to me like there's two spots there, side by side, and not just a single spot, which I'm hoping for. And this can be caused by all of the OPA crystals being off in the same direction from each other. So I'm going to adjust the crystals. First, I'm going to set all the motor errors to 0 so I can see how far I'm moving them. So you can see the delta P here for each one of the OPA crystals is now 0. And I'm going to move each one of these crystals clockwise by 70 some points. Okay. Okay. Now I'll go back and look. It actually did better. Try that again. Yeah. No, I actually think that's pretty good. usually doesn't happen that quickly. You have to iterate back and forth in order to get the beam overlapped. Okay, now you've optimized for collinear phase matching. Okay, now we have the OPA crystal run collinear phase matching and matched to the oscillator at 745 nanometers. This is a very convenient position to check the actual wavelength of the system because there's absorption features in acetylene right at around 742 nanometers. The coefficients for the OPA crystals that I've put in from past work are likely going to be good enough to just get me down to 742. So I'm going to add in the acetylene cell that I've got here and insert block the beam here and put the wavelength filter in so that I'm only passing the mid-infrared. I'll do this in just a second. And then look for the acetylene peaks that I have listed out right here. This is what you end up seeing. But I like to tune in on one of the smaller peaks here whose actual vacuum wave number is known. Okay, I've got the acetylene cell in place. I've got the stack of plates polarizer put in the C configuration, which is passing the mid-infrared light from the system. And I've started scanning already down from 745 fairly quickly, and I'm starting to see the spectral features of the acetylene. The main lump you're seeing there is the main transition peak, sort of like a Q branch. We have the 3 peaks already. This would be number 9, number 8, number 7 that we're seeing on the picture here, and number 6 is coming up, and I'll use number 6 for the calibration. Okay, that is going to be coming up very shortly, so I'm going to stop the recording here, stop the scanning, go down to the smallest rate, and then start again. I don't want to save that data, and then continue on to the blue as we were doing, but at the slowest speed possible. I could actually switch to the scanning setup and go into wave number mode. I can change the base speed here if I want to, but I'm not going to do any of that now. I'll just go at the slowest rate that we have. So start scanning blue. That should have been the peak. Yep, that was definitely the peak, so I'll go back to it. See, we're scanning a little too fast from the power meter, so they're not completely overlapping. I'm going to pick that as the best position. We're at, if I press the F4 key, I'll see where we're at. We're at 740.565577, and what I calculated for this peak was 740.526551. So let me just type in 740.565577. And so I want to go to a smaller value, and so I need to subtract off 0.039 nanometers from the curve. I can displace the curve simply by going into the settings file here and adding in a near IR wavelength offset. So I'll put this in minus 0.039026. And if I've done the sign correctly here, it should read 740.5265277. Okay, fine. 526551. That's what I wanted. Now, that step of going to a known spectral feature, measuring where it is with respect to the displayed wavelength in your system, and deriving an error that you enter in to an offset for the near IR wavelength is all that you need to do to recalibrate the system. That's because we're using the velocity mode. Only the wavelength needs to display correctly. The absolute positions of the motors for the crystal motors do not matter. I can change those values to any value at all, and the system is going to tune in exactly the same fashion as it does. So the offset is the only calibration that needs to be done for the system. So once you have the system up and running at some wavelength and you've optimized it and you can determine what that wavelength is, all you need to do to recalibrate the system is find the difference between the current displayed wavelength and what the wavelength should be displaying, and entering that value in as an offset into the system. Using this velocity scanning mode, I can on the fly optimize energy for the system without changing the tuning characteristics for the system. The tuning characteristics remain unchanged. This is not true if you've got a lookup table, and so and that's why, or one of the main reasons why I chose this tuning method for these systems, is that you don't have to suffer through generating tuning curves every time you want to calibrate the system. Okay, at this point we've done the calibration for the system. We've corrected for the wavelength offset by measuring the absorption in acetylene. The last stage is to calibrate each one of the OPA crystals. Now I'll do it in the same fashion, scanning down to 710 and taking data I don't take it as often for the OPA crystals, like maybe 8 to 10, every 8 to 10 nanometers rather than 5 to 7, but that's a choice up to you, and collect the data. Now I have a wavelength offset that we had discovered for the system using the silver gallium selenide cell, or the acetylene cell, and so when I go through the calibration routine, you'll see how the calibration takes this value into account. Okay, let's say I've collected the data now. I can go into the calibration, generate fits. I've got the new file moparam.dat, and it should step me through 7 motors here. I'll just go through them quickly. It's interesting. There's a lot of curvature you can see for the OPA crystals. There's an inversion point. It's actually, if you were running the OPA crystals as a simple OPO, this would be a very broad bandwidth output, like hundreds of wave numbers. Okay, now I'm ready to save again, but you can see it says bits have been generated with a non-zero near-IR wavelength offset. When using this data, the near-IR offset from the program must be set to 0 for correct operation. Follow those instructions. That's it.